All right, we made it to lesson 1.3 of AP Physics C, Mechanics, and this is non-uniform acceleration, unlike the previous lesson, which was just uniform acceleration. And so this is going to be a really short content review, probably 2 minutes. What it is uniform acceleration had 5 equations that we just used. Non-uniform acceleration actually only has 4, and it's a bit different than usual. So here, the only quantities we're going to be using are position, velocity, acceleration, and also occasionally time, not as important as the other 3. But the 4 equations that we're going to be using are velocity is the derivative of position, acceleration is the derivative of velocity, and then displacement is going to be the integral from t1 to t2, or ti to tf, if that's what you prefer, of velocity dt. And the change in velocity is going to be the integral from ti to tf of acceleration dt. Just those 4, and you can solve the problems. What they're going to usually do is give you an equation for either position, velocity, or acceleration based on time, and then you have to take the derivative or take the integral, solve for the other equations, and then, solve for some stuff they give you. So that's actually it for the content review. I was not lying when I said that it was this short. So time to move on to the actual questions. We have 3 questions here. First one is this. It gives us an equation like I said it would. Now, it does give us in terms of variables, but it just defines the variables immediately after. The reason for this is so that they can include units and stuff like that. It'll look weird because in the second problem they do this, and that looks kind of weird. And so that's why they do it this way, usually. So that's the position equation. And so for part A, we want to calculate the average velocity of the car for the time interval. How do you calculate average velocity? Well, average velocity is just change in position over change in time, which is x final minus x initial over t final minus t initial. Well, we know t final and t initial are 10 and 0. What's x final and x initial? Well, that's why we have the equation. X of t is equal to 3t squared minus 0.11 t cubed. And so when t equals 0, that's going to be 0 minus 0, which is just 0. But when t equals 10, that's going to be 3 times 10 squared, or 300, minus 0.11 times 10 cubed, which is 110. That's going to be equal to 190. So it's going to be 190 minus 0 over 10 minus 0, or just 190 over 10, which is just 10 meters per second. That's going to be your average velocity. For part B, calculate the instantaneous velocity. So that's going to mean we have to take the derivative of position. Velocity, the equation for that is going to be 2 times, because power rule, right? 2b t and so on. And so if we use this equation here, we bring down the 2 and it's going to be 6t minus, bring down the 3, that's going to be 0.33 t squared. Plugging in values, first at t equals 0 is going to be v of 0 is equal to 0 minus 0, or just 0 meters per second. At the second one, v of 5, you plug in 6 times 5 is 30, and then 0.33 times 5 squared, or 0.33 times 25, is going to be 8.25, and so you subtract them and you get 21.75 meters per second. And then part 3, that's going to be v of 10. That's going to be 6 times 10, or 60, minus 0.33 times 10 squared, which is just 33, and that's going to be a total of 27 meters per second. So those are the 3 instantaneous velocities that we calculate. And finally, for part C, how long after starting from rest is the car again at rest? So we want the velocity to be 0 again. And so we just solve for vt equals 0. And so that's 6t minus 0.33 t squared equals 0. Factor out the t, you get 6 minus 0.33 t equals 0. And so 2 solutions to that. First, t equals 0. We already know that. That's when it starts off at rest. Second is 6 minus 0.33 t equals 0. And so you just solve for t. You're going to get t is equal to 18.18 seconds. And so that's how long it takes for the car to reach rest again. All right. Let's move on to the second problem, which is pretty similar. It also gives us an equation. It's just a bit more complicated because it has t to the power of 6 in it, which is always fun when you have powers higher than 3. Position equation is this. So we can rewrite it as x of t equals 2.17 plus 4.8 t squared minus 0.1 t to the power of 6. It looks a lot simpler now. Find the position and acceleration at the instance when the car has 0 velocity. Okay, first we have to find velocity, set that equal to 0, and then solve for position and acceleration. So first take the derivative, and that's going to be is equal to just 2.17. Derivative of that is 0, and so it's just going to be this power rule 9.6 t minus 0.6 t to the power 5, and that's equal to 0. So you factor out a t, you get 9.6 minus 0.6 t to the power 4 is equal to 0. So either t equals 0, which is not really that interesting, but that is a point nonetheless, so we have to consider that. And the second one is, well, you just solve this equation where 9.6 minus 0.6 t to the power 4 equals 0. So you divide it and you get t to the power 4 equals 16. And so t is equal to 2 or negative 2. Time cannot be negative, so t is 2 is our second answer. Now we just have to find the position and acceleration at this instant. First, before I do anything, I'm going to solve for acceleration, the equation first. So we just take this equation and take the derivative of that. So first is going to be 9.6 minus, you bring down the 5, that's going to be 3 t to the power 4. Okay, now we're ready. X of 0 is equal to, well, 2.17 plus 0 minus 0, or just 2.17 meters. X of 2 is going to be 2.17 plus 4.8 times 4 minus 0.1 times 2 to the power of 6, which is 64. That's going to be definitely harder to calculate than the first one. But when you plug it all in, you get is equal to 14.97 meters. So those are the two positions. And then for accelerations, acceleration at 0 is going to be 9.6 minus 0, which is just 9.6 meters per second squared. Acceleration at 2 is going to be 9.6 minus 3 times 2 to the power 4. 2 to the power 4 is 16. So it's going to be 9.6 minus 48, or negative 38.4 meters per second squared. So that's going to be your two accelerations. That was part A. Now we have to do part B, which is draw the graphs of motion. Now, technically, they gave us the answer for part A because t equals 0 and t equals 2. That I know, I didn't see that before, but technically that's true. So for xt, I think it's probably better, actually, if I just do it in the first quadrant. Or here, this is the best way. Because we know we don't need negative time. And so just brief sketch, we know at t equals 0 it's 2.17, at t equals 2 it is 14.96, and we let's actually start with acceleration because it's easiest to find the acceleration. That's just 9.6 minus 3t to the power 4. We can even graph that. So it starts at 9.6 at 0 and goes all the way to negative 38.4 meters per second squared. And so we know it looks something like this because it's in the form negative 3t to the power 4. And so now we know that acceleration is positive here, negative here, and so we can use that to build our velocity graph. We know initial velocity is 0, final velocity is 0. That's the entire point of going from 0 to 2 because velocity is 0 at both of those points. First, acceleration is positive, which means velocity is increasing, so it's going up here. Then as acceleration reaches 0 and goes negative, velocity decreases. So it looks something like this. Obviously not accurate, but close enough. It's a sketch. And finally, we know velocity is positive the entire time here, so position must be increasing. Now, is it concave up or concave down? Well, it starts off concave up because velocity is increasing. Then velocity starts to decrease, so it becomes concave down. And so it starts off like this and then goes something, starts off like this and then goes there. Because it starts off concave up, then goes concave down, but it's increasing the entire time. That's it for our second problem. Pretty long problem, actually. The third problem shouldn't be as bad. It is also a problem where we're given an equation. That's going to be basically all of these non-uniform motion problems. The acceleration is given by this. So instead of giving the position equation, they're giving us the acceleration equation. And they give us the values. The motorcycle is at rest at origin, blah, blah, blah. Find the position and velocity as functions of time. Calculate the maximum velocity it attains. Okay, so acceleration is 1.5 t minus 0.12 t squared. And so you want to integrate it. So this is nice because we've been taking the derivatives before, but now you have to integrate. you integrate this equation, you're going to get v of t is equal to, well, this is t squared, and so that becomes 0.75 t squared, minus this becomes t cubed, so that should be 0.04. You're just dividing by 3 and 2 here. But then there's also that plus c. We know it starts at rest, though, so we can ignore that. It's just plus 0. And finally, well, that's one part. We found the velocity as function of time. For position, we integrate again. Now it should be t cubed, so you divide by 3, that's 0.25. And then minus, this is t to the power 4. Oh, it's such a nice number, 0.01 t to the power 4. And again, it starts at rest at the origin, and so it's going to be plus c, but c is 0, so we can just ignore that for now. Now, it's not always going to be like that, and so be careful to always include the plus c and then solve for it given the information that you have. You want to calculate the maximum velocity that it attains, and so that's when acceleration is equal to 0. So a of t equals 0, 1.5 t minus 0.12 t squared equals 0. Factor out the t, 1.5 minus 0.12 t equals 0, and so you just solve, well, you know t is not equal to 0 because that's when it's at rest. So you do 1.5 divided by 0.12 to solve for t equals 12.5 seconds. Now you want to calculate the velocity at that point, so v of 12.5 is going to be 0.75 times 12.5 squared minus 0.04 times 12.5 cubed. So you would calculate this. First of all, how do you know that's going to be the maximum velocity? Because that's the only critical point, first of all, and you can also solve for other velocities at different times and make sure it's smaller than this one, but usually you want to do that before you solve for it so that you don't solve for the wrong one. But if you do find out, it's going to be 39.06 meters per second. That's going to be the maximum velocity it attains. All right, that was long. The content review was super short. The problems were pretty long, but that is non-uniform motion, and that's going to be probably the most important concept in these first 3 topics. So our next video is going to be about 2D motion and like vectors and stuff like that, so keep a lookout. See you then.